Hello, my friends. I hope you're doing well today. So in the previous videos, we have talked about how to do stoichiometry with chemical formulas, mainly using the subscripts in a balanced chemical formula on a mole basis to relate moles of compound to moles of a particular element. And then we further expounded upon that to go to grams by using molar mass. And then we calculated formula or mass percent. We talked about how to calculate empirical and molecular formulas. Now we are at the point where we are going to do stoichiometry using balanced chemical equations or chemical reactions. So before we start doing mathematical problems or stoichiometry with chemical equations, let's talk about the parts of a chemical reaction and how to balance a chemical reaction. So this example here is just to give you as an example for the nuts and bolts of what a chemical equation or reaction consists of. You have molecules that are on the left side of an arrow. Those are the reactants. Molecules that are on the right side are the products. The arrow means that those reactants have undergone a chemical change to become these products. Sometimes you will see information written above the arrow. That information just has to do with how the chemical reaction is done in the lab. Maybe you added heat, or maybe you added a particular catalyst. If you go on in chemistry, you will start to see more information written above that arrow. You won't really do that in Chem 1. You'll see that more in organic chemistry. What you will see, aside from reactants and products in a chemical equation, although it's not shown in this one, but you will see often the state of a substance that is designated. And again, when we mean state, we don't mean Oklahoma or Texas. We mean solid, liquid, gas, or aqueous. And so you should know the abbreviations for particular states of matter. Fairly self-explanatory for solid, liquid, and gas. What may not be as intuitive is this AQ. AQ means aqueous. Aqueous is obviously something that's in liquid form, but something that is aqueous specifically means that that substance is dissolved in water. And knowing that is going to be important when we get to our second unit, particularly chapter 4, when we start talking about types of chemical reactions. For right now, just know those abbreviations and what they stand for. Know that reactants are on the left-hand side, products are on the right-hand side. In between is an arrow. And you can think about that arrow as like an equals sign because those reactants have been transformed into products. And just like an equal sign in algebra, in math, you can't have things simply appear or disappear. If you add 5x to one side of an equation, you have to add 5x to another side of the equation. If you have two oxygens on one side of the equation, you have to have, on the reactant side, you have to have two oxygens on the product side. So hopefully looking at this top chemical equation, you can see that, oh, this chemical equation, there's something wrong with it. It is not balanced. My number and type of atom on the left-hand side is not equal to my number and type of atom on the right side, or on the product side. And so that's where we have to balance chemical equations. And when balancing chemical equations, always and always forever, amen, use coefficients. Numbers out, let me get my little pointer here, numbers out front of each molecule. So subscripts are used when writing chemical formulas, putting ions or atoms together to form molecules. When balancing a chemical equation, it's always with coefficients. numbers out front of the species. If there is no coefficient present, then that means that there is just one of that species present. And so hopefully you see that, well, okay, if I'm going to balance this chemical equation, well, I've got one carbon on this side, I've got one carbon on this side, 4 hydrogens on the left side, I've only got 2 on the right side. So the only way I can get 4 hydrogens on the product side is to put a big fat 2 in front. That 2 will go to everything that's behind it. Specifically, I now have 2 times 2, or 4 hydrogens. I also, from this 2 waters, have 2 times 1, or 2 oxygens. So my hydrogens are now balanced. My oxygens still aren't balanced though. I now have 2 plus 2, or 4 oxygens. So the only other way to get 4 oxygens on the left is to do a 2. And so what I have written in red is kind of shown pictorially down here. Take home message: balancing chemical equations must be done. The importance of why that must be done will be made apparent shortly. When balancing chemical equations, always, always, always coefficients. So when I did this example of balancing this chemical equation up top, I sort of did it by inspection. I looked and I saw, okay, I've got 1 carbon here, 1 carbon here. I went back and forth. Another way to balance chemical equations is, to keep track of all of your ions or atoms, is I like to do this chart method. This is, I think, particularly helpful once you get equations that get longer. And so I wanted to show this as an illustration for how to balance a chemical equation using a chart method. So what I have done is, for each side of the reaction, for the reactant side and the product side, I've written a little chart that lists the atom or the polyatomic ion that's present. And then I have a column for where I can put the number of that species that is present. So first, after I make my chart, I look to see how many I have of each species before I even do any balancing. Then I balance each atom at a time and change coefficients and my chart as necessary. So let's go ahead and do this example. So on my reactant side, right now I have 1 iron, I have 3 bromines, I have 2 hydrogens, and I have 1 SO4 chunk. Many times it can be helpful or useful to balance polyatomic ions as a unit, as an intact unit. If you wanted to split that up into sulfur and oxygen for balancing, that's fine, but it makes things a little easier since the sulfate stays together on both the reactant and the product side. I'm just going to treat that as a chunk, as a 1 unit to balance. Because on my reactant side, I have 1 SO4 chunk. On my product side, I have 3 SO4 chunks. I have 2 irons and 1 each of the hydrogen and the bromine. So we now have our chart. Now let's go and balance each atom individually by adding necessary coefficients and changing our chart as necessary. We've got 1 iron on the right, or on the left, 2 on the right. The only way to get 2 irons is to add a 2 out front of the FeBr3. That will change my chart, so I now have 2 irons. So I now have 2 irons, which is great, but that also changes my number of bromines. I have 2 times 3, or I now have 6 bromines. That 2 goes to everything behind it in that molecule. Making that change to bromine is important because if I have 6 bromines on the left and 1 on the right. The only way I can get 6 bromines is to put a 6 out front of the HBr. I can't put anything in between. I can't put a coefficient in between atoms in a molecule. So I now have 6 bromines, and hopefully you see I also have 6 hydrogens. So my irons are balanced, my bromines are balanced. Hydrogen, I've got 2 on the left, 6 on the right. The only way to get 6 on the left is to add a 3. That will give me 3 times 2, or 6 hydrogens. It will also give me 3 SO4 chunks, or 3 sulfates. Just go ahead and put a 3 there, and hey, that's going to work out great, because how many sulfates do I have on my product side? I have 3. So I have gone through and balanced each element, or each chunk. Now I'm going to go back and make sure that my columns match for each element. And when they do, that means that the reaction is balanced. So I've got 2 irons, 2 irons, 6 bromines, 6 bromines. Same for the hydrogen, 3 SO4s and 3 SO4s. So that is a balanced chemical equation. Using this chart method, there are examples obviously in your MindTap homework, also on the Chapter 3 worksheet. So I would encourage you, particularly with equations that are longer, when balancing them, to use this chart method.